Okay, good afternoon. So you've had the best paper session. It's now time for everyone else. So I'm going to be talking about planning while the clock ticks. Just to give some motivation about this work, for those of us who ever execute our plans, we might think of a typical architecture as looking something like this. So we have a planner which produces a plan. We give to an executive which starts taking actions in the world, observing the effects, and it might be plan or some other bits and pieces, but we generally have this sort of situation. What about time? So we all know that time is important. If you're thinking about executing plans in the real world, then you usually need to think about time in one form or another. We have temporal planning to deal with actions that have durations and where we need to coordinate parallel activities. Where does temporal planning fit into the sort of execution architecture that I just had on screen? If we plug a temporal planner into the top, so we now have a model which has an explicit notion of time, then typically we'd say, well, time passes in our environment. So we come up with a plan, we start executing it, and then there will be some time will pass between us taking some action and then observing the effects of those actions on the world. What about the time, though, that it actually takes to find the plan? The diagram I just showed you, it's fine if we're in the sort of mission operations planning where right now we are planning for what we're going to do tomorrow, and we are very confident that the time it's going to take to find that plan is much less than how long we have until we need to start executing it. So if I'm going to take half an hour to find the plan now, and I'm going to start running that plan at midnight, that's absolutely fine. But what if we have a situation like this, where we have a robot in the real world, and it will arrive at some situation, observe the state of the world, and then it needs to make a plan and execute it? We can't actually find a plan ahead in that situation. And planning while the clock ticks, the title of the paper, we're dealing with a situation like this. So now we have time passing explicitly in the planner itself and in the environment. So instead of just in the environment, we actually need to think about how long it's taking to plan. This doesn't really matter if you don't have external temporal constraints. But as soon as you have something as simple as a deadline, if you are in a situation, you know you need to plan, and you've got a deadline by which you need to have got things done, the time spent planning matters. So if we say we have a 10-second deadline from now, it's no good spending 8 seconds to find a plan which will take 4 seconds to execute, because by that point we are 2 seconds past our deadline. So if we've taken t seconds to plan, then the plan's make span must be no greater than 10 minus t for us to stand a chance of actually executing it inside the deadline we have available. So we'll talk about the goal achievement time as the time spent planning plus the time taken to then execute the plan. And if that's infinity, that means we couldn't actually achieve our goals within the temporal constraints we had. So my running example, say we land at Schiphol Airport at 6 o'clock in the morning, and we have a new border security test where we have to solve a Rubik's Cube before being able to clear immigration and enter the country. So let's say we land at 6, we then have to solve a Rubik's Cube, and then we have to get to Delft. And we have a few options. We can get a train which leaves at 6:30, we can get a train which leaves at 7:30, or we can get a taxi at any time. It takes about 35 minutes. If we knew what the Rubik's Cube was going to look like, we could solve it on the plane, land at 6 a.m, start executing our solution to that Rubik's Cube puzzle, quickly get through border security and get to Delft on time. However, if the Rubik's Cube is only revealed to us when we land, then we can't plan ahead. We can only plan when we've observed the situation, and then the planning time matters. So I'm going to be talking about situated temporal planning, which is this sort of paradigm. A lot of planners use simple temporal networks to manage their temporal constraints. Optic, Popov, planners I've worked on in the past, and a range of other planners. The 0 point is what I'm really interested in. So normally in these planners, the 0 point is when you take the first step of the plan. So that you run them, they print out a solution, the first action is at time 0, everything else is relative to that. Now, because we're thinking about planning time, we modify our STNs to actually have 3 separate explicit points. First of all, our 0 point is the time at which we start running the planner. Second, we have the current time, so now. If we have been planning for 3.5 seconds, then now is 3.5 seconds after our 0 point, so the time at which we started running the planner. And then we also have the plan execution start time. All actions that we actually take come after the plan execution start time, but all the absolute temporal constraints, all our deadlines, all our windows in which we can do things are relative to our 0 point, the planner start time. We know how long it's been since we started running the planner. What we don't know is how long is it going to be between we are somewhere in search and we will have a solution when we can start executing it. We can estimate that, I'm going to talk about that in a bit, but essentially this is what we're working with as a framework. As a trivial modification, we can modify search so that if we had a timed initial literal which was going to happen at time 6, and it's now time 6, well, we can force that to happen. That's obviously something which would have to be in the plan because we've not found a solution yet, so that is going to be forced upon us. So if we update our STNs, we can prune search nodes with inconsistent STNs, because as soon as we have this effect of now is pushing everything later and later in the start, so it can't start at 0 anymore, that's going to actually allow us to prune some states which would lead to plans which could never actually be executed. I'll give you a concrete example. So let's say we're going back to our Rubik's Cube problem, and we're going to build a simple temporal network for taking train 1. So we landed at 6, and we've been planning for 31 minutes, and we finally found a solution. So at 6:31, we can now actually start executing our plan, and then we can take the step of boarding the train. The problem is that's inconsistent because that train left at 6:30. And if you follow along the top there, we have a minimum amount of time of 31 minutes because it includes the planning time. And along the bottom, we have a maximum amount of time of 30 minutes because that deadline was set to relative to the time at which we ran the planner, not the time at which we started executing the plan. So we can straight away recognize that this is no longer an option. What about the remaining search time? Now this will work if we've already passed the point at which it was too late to do something. What if we've been planning for a bit and we reckon we won't be able to actually board train 1? How do we actually try and estimate the remaining search time? And can we actually put that into the STNs? Well, we can put it into the STNs, but because it's an estimate, we can't safely prune with that in the STNs. We can't say absolutely, we think it's going to take us about 30 minutes to solve a problem. We can't use that to say, well, it's going to take 30 minutes, we're going to prune that. It wouldn't be safe. So we use a bit of a trick which is popular in classical planning. We have 2 open lists. We have our priority open list, which is ones where the STN is satisfied, including our estimate. And we have another open list where we didn't put this estimate in and the STN is satisfied. So if you are familiar with the concept of preferred operators, you can say that a state which has the STN satisfied with our estimate of remaining search time, that's the preferred operator state. How do we estimate remaining search time? So there's some work by Dion, Thayer and Ruml, where you essentially plug together 3 numbers. The first one is the expansion delay, so how many nodes were expanded on average between a node being put on the open list and then later being popped off the open list. Second is, how many nodes are we actually expanding per second? So is it, typically in our test, we might do 50 or 60 expansions per second. You put those together, you're working out how long is it taking in seconds between a node going on the open list and coming off. And finally, how many expansions are we going to have to do to get from a node to a gold state underneath it? Best case is the heuristic value is an indication of how many expansions we need to do. Put those together, you get an estimate of the remaining search time. So now if I come back to my little train example, if we've been planning for 5 minutes and our estimate says that it's going to take 30 minutes to reach a solution plan, then we would say boarding train 1 is inconsistent. But it's only inconsistent if we include this estimate there of saying that it's going to take 30 minutes to reach a goal state. That's only an estimate. So we would put it on the all queue, but we wouldn't put it on the on-time queue. So far, the only thing I've used from my heuristic is the number of actions to reach the goal. But if I actually look at the actions in the heuristic, I can get a bit more insight. So we're using a relaxed planning graph heuristic. If we look at the actions in the relaxed plan, we can actually say, well, these actions in the relaxed plan have deadlines on when we could apply them. And it's reasonable to suspect that the relaxed plan is indicative of how we would actually reach the goal. So we can estimate some further deadlines on our solution space by looking at the actions in the relaxed plan. Again, this isn't admissible. We can't do hard pruning on this, but we can at least use it in our priority open list. So our on-time states, we can say it's on time even if we include the extra actions from the relaxed plan. So if I stop trying to board train 1 and I now try and board train 2, let's say we are part way through search. We've been searching for 31 minutes. We are going to add to the plan the action to board train 2. This seems okay so far. Right? The train doesn't leave until 7:30. We've already been planning for 31 minutes. But not in the plan yet is this next action, which is to actually arrive in Delft. And this action to arrive in Delft had the deadline of we can't do it later than 8 o'clock in the morning. So this action is in the relaxed plan. We can pick up the deadline from that and say, well, including the relaxed plan, it's not a consistent solution. So this would go on the all queue, but not on the on-time queue. So it's all about trying to squeak better estimates of whether this partially completed plan is going to reach the goal in time into our priority queue system. So a bit of evaluation. We had to think about what do we actually compare this to. And the most sensible configuration we could come up with is if you are assuming you know how long it's going to take to plan. So you have allocated yourself a budget for planning time. So as our baselines, we took a number of configurations of Optic, which is the planner we built on, and we allocated it a certain amount of time for planning, so 5, 10, 15, 20 seconds. And the effect of that, when we look at the domain, is that all the deadlines get pulled back by that amount of time. So if we have a deadline at 120 seconds, and we are allocating ourselves 20 seconds for planning, then in effect we have 20 seconds to find a solution, and then 100 seconds to actually execute it within that deadline. So you pull the deadlines closer to 0, the more time you have to budget for planning. Then compared to that, we had 3 configurations. One is, we call it time aware. So no estimates, no estimated remaining search time, just as straightforward. If it's too late already, you can prune a state. Number 2 is using dual open lists and using the estimated remaining search time. And then time predictive plus is also saying, well, we can plug the relaxed plan in and get a more refined estimate from there. And in all cases, we stop when we find our first solution. We took IPC benchmarks which have tills, not so many of them, but we used all of them. And we took some problems from the RoboCup Logistics League, which you probably heard about slightly earlier on this afternoon. Our measures, number of problems solved, standard IPC score, average planning time, and also this goal achievement time, so time taken to find the plan, plus the plan make span. And here's what it looked like. So if you have a fixed budget for your planning time, then actually you do much worse than if you have any one of our time-aware configurations with our super fancy version, with all the estimates we could think of thrown in, doing slightly better than our more bare-bones option there. But even the bare-bones option, just taking account of how long you've been planning for, does very well. If you actually look at these data in some more depth, you essentially get a somewhat intuitive situation of if you guess the planning time, and that planning time is actually close to the time it really did take to plan, which you don't actually know in advance, but say you were lucky, then the right thing to do is to have a fixed budget. If you can guarantee something about your problems where it's always going to take about 5 seconds to solve them, then just give yourself 5 seconds to plan. But generally you don't know that, and there's no way you can guarantee it, so that's where actually having a time-aware planner pays off. In a RoboCup Logistics League, the results were less clear-cut. There was no one planner that solved all the configurations, so slightly worse coverage for time predictive plus there, but it solved some problems that the other didn't. We can't actually throw a portfolio at this. because we are actually doing situated planning, we have actual deadlines. So unless we start thinking about we're going to actually run each one for a tiny, tiny amount of time, we can't actually use a portfolio. We have to try and find something which gives good average coverage. And again, the configurations where you have to guess what the planning time might be did much less well. So, conclusion, well, time flies, it's up to you to be the navigator, is an aphorism for the day. This is the first step towards online planning and execution, so actually accounting for the time it takes to find a plan as part of your operations. It's an interesting problem to work on. We can adapt existing temporal planners, so in our case we took Optic and we fiddled with its SDN, and we brought in various other estimates. Still a bit of a way to go to get really good performance, but it's a really interesting field to be looking at. Thank you.
All right, we've got time for some questions.
Yep.
Have you thought about executing part of the plan while you're still planning?
Yes, so one of our bits of future work is, do you really need to find a complete solution plan before you can start execution? So we have some ideas which one of my RAs, Moses Martinez, did in his PhD thesis, was on variable levels of abstraction for planning. So you come up with a fine detailed plan only for the next period of time, and then you have a more abstract plan after that. And if we can commit to a fine detailed plan, then yes, we can actually start executing sooner. Yeah.
All right, and another problem might be if actions take more time than you would anticipate, because
Yes.
here you kind of assume that you
Yes.
know how long things will take, right?
So right now we are not dealing with uncertainty, you are correct. We would replan in that situation. There isn't a nice way in PDDL to kind of express the objective function, but you want a plan with lots of slack for execution time. If that's something you're interested in, come and talk to me, because I've got a student who's starting to look at that now.
Third thing that
Yeah,
came
why
to my
not?
mind, but maybe I can...
No, go for it.
No, I forgot. Do you really have to commit to a train to take before you have solved your planning problem? Or could you just decide to commit later to the train and then this whole issue would go away?
So the plan contains some action to board a specific train. And as soon as you add that action to the plan, you've committed to a certain action being executed at a certain time. If you want to use a different train or if you want to get a cab, you would put a different action into the plan.
All right, thanks.
All right, let's thank the speaker one more time.